All right. Good morning, everyone. Welcome to our last class in March, Wednesday, March 30th. Week 11, lecture 1. So we only got a few weeks left. I think, like 3.5 after today, basically. Anyways, per usual, going to go over the whiteboard, some due dates, some assignments rolling back in, like Excel assignments and quizzes that we warned about. So 4.4, 5.1, 5.2, those had all been previously discussed. I said we are still going to cover one quick guided activity problem today, but 5.2, the material was essentially finished last time. So those due dates are the 30th and 4th, respectively. Then 5.3 we'll knock out of the park today, so we'll call that due in a week on the 6th. We're also going to assign the next Excel file, 5.1 lines. That one's not too bad, due in a week. Then video quiz 2, we're going to say is also due in a week on the 6th. So 5.1 Excel lines and video quiz 2 will be due on the 6th. So we haven't had one of these video quizzes in a while. This is our, I want to say like 6th quiz in total, but it's the second quiz based on the videos from my math lab. So we've talked about how to find those. You go to your resources, and this will be on chapter 2. So it's specifically on chapter 2 videos. So when you open that file, it'll tell you which specific videos to watch. It's either 4 or 5 questions. These video quizzes are always either 4 or 5 questions. You type up your answers or handwrite them and take a picture, whatever you like. Sentences, paragraphs, couple of words, whatever. Make sure they're in your own words. Do not literally copy verbatim what the author says. That is plagiarism. Put it in your own words. And then there's a spot in Canvas to download the file and a spot to submit the file. We're going to do several of these types of quizzes back to back. I wanted to do one on chapter 2 just to go back as kind of a review type quiz, just to remind us of some stuff. But then the next 3 will be on chapters that we're working on concurrently. So I think the next one will be chapter 6, then 8, and then 9, something like that. It doesn't matter. We'll see when we get to it. And then a reminder, your project. So you've only got 2 days left to keep track of your expenses today and tomorrow. And hopefully you've already started building that Excel file because that's going to be due on the 6th. And you've got other things due on the 6th as well. Remember, we said you could be building that Excel file all month long. You didn't have to have every single one of your expenses in order to build the Excel file. Once you add a single expense, and honestly, you don't even need that, you could have started building the Excel file. Remember, if you email me the day before it's due, I'm not going to promise to respond to anything about it. I might get to it, I might not. And also the questions that I will answer about the project are very, very, very limited, as 1 or 2 of you already know who have emailed me. Make sure you understand what you are responsible for the project. The file goes into great detail about what you have to do, the like roughly 6 different things I grade on essentially. And make sure it's your own work. Make sure you had started with a blank Excel file when you began. All right, so with that being said, let's go ahead and pick up where we left off with that guided activity in 5.2, and then we will dive into 5.3 immediately after. Very end of 5.2, doing a guided activity. It's the intercept one, and it's page 204. That's too far. Here we go. All right, so for this activity, in the previous one we had done, we had figured out what the slopes of those were, and then we started talking about using that cookie cutter phrase, like the output is changing by this value, which was the slope, and then you go y units per x unit. That's what I mean. Now we're just going to talk about the intercepts. It's going to be a much easier way of saying things. It's going to be a much easier problem to tackle. So we'll go through these pretty quickly. So they're asked to interpret the Y-intercepts, and let me do, so I don't have to keep going back and forth on that. Sometimes it's worth it to stay on that screen. Sometimes it's better to do things like this. What? Where'd it go? Technology, man. Okay. So this worksheet asks you to interpret the Y-intercept. So we've said the Y-intercept is often interpreted as a starting value or a fixed value. Starting, another word of that is initial value. There's a lot of different ways to say the same thing in the real world, of course. So let's go ahead and get it.
We have our 5-cent plan where we were paying 5 cents per minute, but then we also had that $20 fixed cost for fees, taxes, whatever. So we said the equation that we developed was y equals 0.05x plus 20, where x would be the number of minutes and y would be a cost in dollars. We used C and M when we actually wrote the equation, but I did say that we could use y and x as long as we wrote somewhere what y and x are. Now, when you have axes set up, this actually is declaring what the x and the y is by just writing y equals 0.05x plus 20 and then seeing minutes on the axis, the x-axis, dollars to the y-axis. That implies that that's a cost and a number of minutes. All right, so just the y-intercept, which is the starting value, also the constant, the fixed value, so that's the 20. So if we're in 1a, the y-intercept is the 20, which is a cost. So the cost is $20 when 0 minutes are used. This is an initial fee. Guess I could have typed that, oh well. So this 20, that's the fixed or initial amount. It just depends on context. Here, I could call it either. It doesn't really matter. I think most of us would call it a fixed fee, but you can also call it an initial fee because it relates to 0 minutes being talked. And then, like we said, we can always see that value on the y-intercept. Now, we've talked about how in real-world models, these don't always have to make sense, and maybe we'll get to that today. All right, second one, concentration of pollutants. And I don't know why they say there's an A and a B and or anything like that. It's just A for all of these, so I guess I can just go number 2. For the concentration of pollutants, so we said there was an initial spill, and then over time, over some days, that spill gets weaker and weaker and weaker because it's diffusing, dispersing, whatever D word you want to use. And that rate of diffusion or dispersion was 0.8 parts per million per day. And that was the loss because it's a negative. But we're not asked to interpret the slope here. We're asked to interpret the initial value, which is the y-intercept, which is 100. So that says that the pollution is 100 parts per million on day 0. In other words, this is the initial spill. For number 3, our Houston population. And I want to point out something on this one. They give you 2 different versions of this. The top one is what you would see. I thought I hit annotate. This is what you would see in Excel. And the bottom one, this is what it would actually be. So we talked long ago about how Excel sometimes will display a number that's rounded, but it actually holds the actual number in the equation or in the formula or whatever it is it's using in the cell. So it'll display this, which makes you think that it's really just 5 million. But the actual number that is stored inside of Excel is this 4.715407 million. So when it does any calculation, and when you throw in any year since 2005, 10, 22, 39, whatever, it is going to plug it into the bottom one. But again, when we visually see the equation, it's only going to show you this one. Now we can double click the cell, and up in the formula bar, we'd probably see that 4,700 if this was in a cell. Unfortunately, this isn't in a cell, it's in a chart, so that might make it a little more difficult to see. But don't really worry about that because we're generally not going to be dealing with these big giant numbers in our homework problems. So interpret, and they say please interpret both. I'm not going to interpret the top one because it's honestly pointless. It's just you're using a rounded number of 5 million instead of the actual number of 4.7 blah 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 million. So the, oh yeah, clear screen, go off of that. All right, so the population of Houston, well, that's the fixed or initial amount, is the 4,715,407 people. At Year what? At year zero? Because we always say it's at the zero amount, so you might go at year zero, and that would be wrong. Because this model is not using years as the independent variable, as the x. You might go, yes, it is. It says years right there. But it's not just using years, it's using something more specific, years since 2000. So if we said that the Houston population was 4.7 blah, blah, blah million at year zero, that's not going to make any sense for several reasons. First of all, Houston wasn't around until at least 1776, and I think no one's going to have a problem agreeing with that. I don't know the actual the year Houston started, so please don't quiz me on my history. And that's not the point of this, but it's clearly, you know, somewhere in the 1800s, because that's when Texas was established. We weren't really heading west until sometime in the early 1800s, right? All right, so we can't say it's at year zero, but that's because this is years since 2000, so that's really at the year 2000. This is a very, very common way of doing a population model. That way we can make it a simple model like a line instead of a more complicated model like an exponential, like we'll see in chapter 6, or even worse, like a logistical model, which I'll never even show you in this course because it's out of our pay grade. So you have to be careful when you're dealing with models with years since 2000. If this was not a model that had years since 2000, if it just said years, I can tell you there's going to be problems with this if you trace it back to year zero. All right, so number 4, last one, that monthly interest. Now, we talked about how this is scientific notation. If that was a plus 11, that means the decimal will go right 11 times. But since it's a minus, the way scientific notation is, it goes left 11 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's a whole lot of zeros, 10 of them to be specific. So that's 0.000000, that's 6, 7, 8, 9, 10, 2. That is the initial amount. Now this Y, this output is in dollars. So this is $1. I don't want to have to write that number again. So this is the interest on the initial amount on the bottom based on monthly balance. So that would be on $0 invested. Now here's the thing. We've said that interest on a very basic level, when we look at just one period, so a year, a month, a day, depending on how it's divided up, and we'll start getting into that more and more, it's just the product of the balance and the periodic rate. So if the balance is 0, 0 times anything is 0. But Excel, for some reason, instead of saying 0, they've given just this ridiculously tiny number. And that's because Excel makes microscopic boo-boos here and there, because it was trying to take a bunch of points and actually make this equation. And in that process, if we had maybe placed one of those points just a microfracture hair off, it would have caused that little rift, so to say. So this should really be $0. When I say this, I mean that number. Because how in the world is anyone going to get $0.00000000002? That's not even cents. That's not even hundreds of cents or thousands of cents. That's like billionths of a cent. No one's going to give you that. It doesn't exist. It's just 0. That's a situation where we have just a ridiculously small number. You just go ahead and call it 0 for the real world context, which makes sense because if you have $0 in a savings account, nobody's going to give you $0.0000002. They're going to give you nothing. Good day. And yes, that was a silly reference. Sorry. I can't help it sometimes. All right. So, something I wanted to point out, these graphs, we know how we make these graphs. You've had lots and lots of practice in Excel with this at this point, so I'm not going to remind us how to do those graphs. You would just have a table in Excel, you highlight them, and then you do insert the suggested chart if they give you one that's suggested, or you can just go to the pre-made layouts and pick one from there. Again, if any of this is not striking a memory, go back to the first week and a half of class videos and rewatch those, please. But how do we get these equations? Because that's going to be extremely helpful to know, maybe for homework, maybe for just working with things in class. And here we go. How to add a trend line and the equation and R squared. R squared is going to become later. I'm not going to talk about what it means yet. But this R squared value, we're going to talk about in chapter 8, which is not that far off. Chapter 6, we're going to be able to knock out in 1 week. And then chapter 8, we'll actually be able to knock out in 1 day if all goes as planned. Chapter 8 is really short. It's only 2 sections. Chapter 6 is 2 sections. Chapter 8 is 2 very short sections, in fact. So you highlight your data and your labels. You insert your scatter plot. I mean, that's literally what I was just talking about for making the graph. And scatter plot is what will make it look like dots. Then you go to add chart element and trend line, then linear. Linear makes a line. If you go to add chart element and then trend line, you'll see other options, and you don't have to make a line, but that's what we're going to be doing for now. And then add chart element, trend line, more options to display the equation and the R squared. So where are you? I'm not seeing it. You know what? I don't want to have to go on a wild goose chase. I'll just make one up on the fly. So let's just go X, Y. I'm not doing any context. We're just going to go numbers. And let's say if X is 0, Y is 2. And then if X is 1, Y is going to be 7. If X is 2, Y is going to be 12. I'm making a pattern here. Just trust me that it's right. And then 17, and then 4, and then 22. Now, when we're talking about real world values, they don't have to be exact fits of a pattern. When we talk about modeling things that have actually happened, it doesn't always have to see that constant slope. Every time I'm going up 1 in the X's, I'm going up 5 in the Y's. They don't have to be that. This 12 could be a 13, this 17 could be a 16, this 22 could be a 5 million if it really just didn't fit the pattern. Again, in a real world context. So let's see if we can follow what all this says. Let me do this, and then that was not what I meant to do. How many times do you hear me say that a semester? This is a joke, but I could make like an extra credit problem out of that. Someone go back, count all the videos. All right, so highlight the data and the labels. So I just called them X and Y, apples and oranges, whatever. Insert scatter plot, insert. And then let me just maximize this for a second so I can see it a little clearer. All right, which one's the scatter plot? Which one's the scatter plot? It's the one that looks like dots. I pointed that out over there. So insert scatter plot. It's generally the top left one. You don't want to do any of this weird stuff. And you might say, well, why wouldn't you want the one that's already connected? Because this is going to connect them perfectly, and models don't always connect perfectly, as we'll start noticing. All right, so there we go. We've got our chart, and we just kind of squeeze that over there. Then we say to put in the line, you go to add chart element, trend line, linear. Make sure you're taking these notes down. So add chart element, trend line, and then there's a few options, and I'll even show you how they look. So look at the graph as I'm doing this, and I'm sorry that I'm covering up part of it, but I can't help that. Linear forecast is the same as linear, except it kind of extends it out further. There's no reason that we ever use that in this class. Moving average, this is really useful for modeling population dynamics, maybe like how many people have had a virus. So they'll measure it every single day, but the measuring is consistent. Maybe there's no measuring on weekends. So looking at the day-to-day chart isn't exactly a great model. So people will just say, all right, I'm going to, at each point, I'm going to average the 5 days prior and the 5 days ahead, something like that. It doesn't have to be 5. That number is chosen by whoever's doing it. And then it gives you a moving average, and you can see this one doesn't even look like it makes sense. So let's not do that. Let's go with linear. Boom. Now again, because this is a perfect model, these fit perfectly. They do not have to. Then to actually see the equation, we go to add chart element, trend line, and more options. So add chart element, trend line, more options. And then a menu pops up over on the right. And then you'll see down here, you can display the equation and display the r squared. Now, again, this r squared, we're not really going to do this until chapter 8, but I like going ahead and pointing it out while it's relevant. So display the equation. Now, this menu is covering it up, but it did pop up right there, and I don't want to close this yet. Let me maximize it. Okay, perfect. So there's the equation. And then if I display the r squared, what this is a value of is it shows you how well the data fits. And admittedly, I'll go ahead and tell you 1 is a perfect fit. So if this data did not fit perfectly, it would look quite different for that r squared. I'm going to copy paste this. Copy, paste. I'm going to make another one of these, but I'm going to make the y values not fit this perfect as x goes up 1, y goes up 5. Let's make this a 6. Let's make this a 13. Let's make this a 19. And then let's keep that at 22. So I'm going to highlight, insert, scatter chart. Pick the top left one. See, this doesn't look like a perfect line. It's kind of close. You could probably, do a nice spitball guess there and it would hit some or most of them. And we'll start talking about that later. But for now, all right. So we got our chart. Make sure you click the chart so that you get the add chart element. And then we're going to add the trend line, linear. And look, see, that one's not a perfect fit. See, this is the first one. This is the second one. When I click the chart, it shows you which data is being highlighted. See, that's not a perfect fit because this was not a perfect model. And now when I go to insert the extra stuff, the equation and the r squared, you can see that the equation has some decimals in it now because, well, first of all, it wasn't that as x goes up 1, y goes up 5. It was never consistent. So they're just making a kind of a best guess. Excel does lots of crazy math to get that equation. Please don't worry about how we get that. It's insane for us. It would take me a month to teach it and to get you to be able to do it perfectly. And it's extremely time consuming. This is why you go, thank you, Excel. I love you, Excel. And then the r squared, 0.9849. That's pretty good, but it ain't perfect. Again, 1 is perfect, as we'll discuss in chapter 8. So just kind of foreshadowing some things there. All right. Cool. .3, I don't really have a lot that I have to go over in this because I've already gone over almost every single one of these aspects with you. So this is not going to be seen very long. I'll put a couple of graphs up here as reminders, but again, this is nothing new. I have already talked about all this. I don't really know why 5.3 is a section besides the guided activities, but it is what it is. And I'll talk about that in a minute, but the Y-intercept of a proportional relationship is 0 and generally not written. So that's when your line goes through the origin, and it doesn't have to go up. It could go down instead. This is proportional, which means your equation just ends up being y equals mx. It's just a number times x. You only have just the variable amount. There is no fixed or initial amount because it's a 0 and nobody is going to write plus 0. On the contrary, when it's not going through the origin, that means it's not a proportional relationship. It means there is a non-zero initial amount. So this is not proportional. And it has the full mx plus b, the mx being the variable amount and the b being the fixed amount. And again, for this first one, the y-intercept is 0. Y-intercept, excuse me, I forgot to write intercept. For this one, it's b. So this height right here is b. So remember your slope-intercept form is y equals mx plus b. That mx is the variable amount, the b is the fixed or initial amount. And we've already talked about how if you know any slope and any coordinate, you can plug these 3 numbers in to find b. Again, we did an example like that last class. I'm not going to do it again. Like I said, most of this is just retreading. A couple new words, though, coming up. The larger the value of m, the steeper the line. So again, that's something we already talked about. If we have a line that looks like maybe this, let's say this slope is +1. I'm going to specifically write the positive. You normally don't, but I'm just being meticulous. Then maybe this steeper line would have a slope of, say, +3. Or maybe your line is pointing down. This might be a slope of -1. I'm not caring about the intercepts here. But then this steeper line might have a slope of -2 or -3 or -4. I'm just going to go with 3. Again, nothing new there. Retreading. This is new for the chapter. This is nothing new in terms of techniques you should be able to handle, but this is new for the chapter. If you're given an equation that's not in this y equals mx plus b form, that's what I mean by in this form. By this form, I mean this form, where it's solved for y. If you have an equation that's not solved for y, it's probably a good idea to solve it for y, because that's what enables us to graph it much, much easier. Yes, you can graph lines that are not solved for y. Yes, if this was an algebra class, I would teach you how to do that. This is a quantitative reasoning course, though, so we like to keep things in common forms, and that way it's as simple as possible. So just solve it for y if you get one. So for example, if you had 2x plus 5y equals 10. So here's your mathematical model, but it's not in an dependent, independent kind of situation. It's not just saying y is this thing based off of this other thing. It doesn't say apples equals blah, blah, blah in terms of oranges. It says if you took 2 times the number of apples plus 5 times the number of oranges, you should get 10. Doesn't have to be apples and oranges. You get my point. So we just solve it for y. I like to put a little dotted circle around the thing I want to solve for. Now this 2x, you're just pretending like it's a constant. You're going to move it over like it was just a 2. But it's not a 2. I don't want to put it under the 10 because those aren't like terms. I want to kind of stuff it to the side so that these 2 x's cancel and you get 5y equals, and then that's 10 minus 2x. Now again, I like to remind myself what I'm solving for. Now I want you to pretend that this other side is just 10. If this was 5y equals 10, you would divide both sides by 5. That's exactly what you would do. Everyone should understand that. But the right side is not just 10, it's 10 minus 2x. Do you know how much effect that has on what you do algebraically? None. You do the exact same thing, except you want to do it like this. You want to divide every single term by 5. See, doing this, I'm going to change colors just because I don't want to have to do that again. This is the same thing. It's the same exact thing as this. Dividing the entire right side by 5 is the same as splitting up the division. But if you do it this way, you're probably likely to want to say, oh, this 10 and this 5 reduce to a 2 and a 1, and that's wrong. They don't reduce to a 2 and a 1 in that form. You cannot do that, you cannot do that, you cannot do that. But when they're split like this, you can. These 5s will cancel. This 10 and this 5 do make a 2, and then you leave that piece with the x alone, and you get y equals 2 minus 2x over 5. Or if you want this to look more proper to have the x term first, that's y equals negative 2x over 5 plus 2. These are the same thing. They are just written in a different order of terms. And you might be thinking, well, Mr. Beckner, why isn't this positive and this negative? Why did you move the location of the minus? Because the minus goes with the x term, so the minus has to stay with the x term. This 2 was positive, so that needs to be a plus. So in this form, you can see that the m is negative 2 over 5, and the b is 2, which means this is your variable rate, and this is your initial or fixed amount. You can't see any of that in 2x plus 5y equals 10. You can't tell me the rate at which this thing is changing. You can't tell me what it started at. It's no good. It's not helpful for us to interpret it as a quantitative reasoning student. Again, sure, you can graph 2x plus 5y equals 10 in ways without doing anything to it. But we're all about the interpretation. We're all about seeing that, okay, every time x increases 1, the y is decreasing by 2/5. Or you can say that the slope is you're going to go right 5 and down 2. And we can see that we initially have 2 of whatever this thing is we're talking about. That's where this is helpful. All right. And then just a couple last minute words. Again, everything after what I have highlighted here, nothing is new. We've already talked about that. Accumulation just means you have a positive slope. Depreciation means you have a negative slope. Those are just two words you might see in the real world or in a QR class. Okay, so this thing is accumulating at this rate. That says it's going up. Or this thing is depreciating at this rate. That means it's going down. So if you're talking about your home in the long term, your home will accumulate value as long as you're maintaining it. If you're talking about your car over a long period of time, your car is going to depreciate in value because car values go down and home values go up on average in the long. Now, yes, if you have got some 1968 Shelby GT500 with a 428 under the hood, blah, 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 car stuff. Sorry, I love old muscle cars. That car is going to appreciate in value because it's rare, it's highly sought after, it's cool, whatever. So yeah, there are cars that do appreciate in value, but if you've got a 2005 Honda Civic running around, trust me, it ain't going up in value tomorrow or a year from now or 5 years from now. Now, it's a Honda Civic, so it's not going to depreciate nearly as much as, say, a Volkswagen Jetta. Yes, I am going to fire some shots at them. All right, enough fun. Again, this part, the sloping, rise and run, we've already talked about that. Not going to talk about it again. Just a reminder. And that closes out 5.3 in the notes, arguably. That's all the notes for 5.3. However, dramatic pause. We do have more of these guided activities I want us to do. And it is not that one. I'm on the next page, sorry. Here we go. Oh, I don't know why I said that. We never even started the guided activities for 5.3. My bad. So we're done with the notes. We got guided activities. But the point of what I was trying to say there, sorry about that, is these guided activities say 5.3, still 5.3, still 5.3. These guided activities say 5.4, and you'll notice it says statistics. And if you remember, I've said we don't cover anything with statistics. However, whenever they modified this workbook, so we got a new version in 2019, they put stuff that was in 5.3 and 5.4 in the guided activities that doesn't need to be in 5.4. So we are going to talk about some of this stuff, most of this stuff, in fact. However, we're not going to be doing any statistics. This stuff that you're seeing right here should still be part of 5.3 in my opinion, so we will still do this guided activity. That's the only time the entire semester that happens. And that's just because, in my opinion, the textbook company made a mistake in organization. All right, so let's leave that for now. Let's get back to the start of 5.3. This stuff, they're just talking about how equations can be written with C and M, letters that are much more tactile for the problem. And these were all things that we saw before. But they could also be just used in Y and X, as long as somewhere on your own you're writing what X is and what Y is. So this 1 is the same as this 1. This 2 is the same as this 2. This 3 is the same as this 3. And you might say, well, hold on, number 2, they swapped the order. Well, we just talked about that in that very last example we just did, that 100 minus 0.8x is the same thing as negative 0.8x plus 100. Oh, Mr. Beckner, this is 0.5% and this is 0.005. Well, 0.5% converted to a decimal is that. Please don't ever write equations that aren't in Excel this way. Please don't ever do that. If you're writing an equation that's not in Excel, make that 0.005 and then your B for balance. This is just silly. Okay. Small numbers, fuzzy numbers. The following table shows Palm Coast, Florida as the fastest growing metropolitan area from 2000 to 2010. Fastest growing, meaning that their population is growing the fastest. I didn't say anything different there, did I? No, but that was intentional. It means that if you look at the change from 2000 to 2010, that it would be the greatest. Now, does it have to be the total change or the percent change? Well, let's just see where we are and if we can figure out which that is. So most populous, so these are the highest population places. So we got New York, which went from 18.3 million to 18.8 or 9 million, depending on how you want to round, which was an increase of about 574,000, which was an increase of 3.1%. So this is just total change and percent change. That's what both of these are. These are total change, which is new minus old, and then this is percent change, which takes the total change, this 574, and divides it by the original of the 18.3 million. So that's how both of those columns are accounted for. The difference of new and old, and then the fraction of the change to the old converted to a percent then. So if you look in this table, the biggest difference you see is 1.23, and that's for Houston, Sugarland, Baytown. I don't know if that's a T or an L. I can't read that. It's too fuzzy. They need some 720p charts in this thing. So that's got the biggest total change, but they said Palm Coast, Florida is the fastest growing. So I guess we're not basing this off of total change. Maybe we're basing this off of the percent change. So let's see, percent change. 92%, that's the largest one out of all those. And look, it's Palm Coast, Florida. So when they talk about fastest growing, they're talking about relative to the size, because Palm Coast, Florida only increased by 45,000, whereas New York increased by 574,000, and Houston increased by 1.2 million. So those were bigger changes, but when we consider relative to what's already there, relative to the original size, this is the fastest one, because look, this was about 50,000, this is about 100,000. It almost doubled in 10 years. New York did not almost double in 10 years. It didn't even come close. It barely added on to the population. So that's because New York is already pretty well established, whereas this Palm Coast, Florida town is pretty new, and you've got good construction crews in there, good politicians, low tax rates maybe for local regions, things like that, that are just kind of initiating growth. And maybe in the next 10 years, maybe right now, maybe this population is 150,000, maybe it's 200,000. I don't know. I'm not going to pull up the data. All right, so what's the point of this problem? We got lots and lots of different areas, cities, whatever you want to call them, because some of these are like, you know, several cities lumped together, just metropolitan areas, kind of like Hampton Roads is a metropolitan area composed of Suffolk, Portsmouth, Chesapeake, Virginia Beach, Norfolk, Hampton, Newport News, and yeah, that's it. I said them all. So use the values in the table to determine the linear equation of the form y equals mx plus b between the 2 points for Palm Coast, Florida, where x is years and y is population. So they're telling us they want our independent variable x to be the number of years, not years since 2000, just years, and then y will be our population. Okay, so we're using these two numbers, the 49,000 and the 95,000. So how do we come up with the m and the x and the b? Well, y and x are going to be just numbers. I'm sorry, what did I just say? Y and x are numbers? No, y and x are going to be the variables in the final equation. It's going to be something like y equals 3x plus 5. That's what we're after. But to calculate the m, we need to know the slope. The slope is the rate of change. It's the change in the y values, which is the population, over the change in the x values, which is the years. So our slope will be the change in pop, new minus old, over the change in years, new minus old. So for this problem, our m should be the change in population, which is 95696, minus the old 49832, then over, and the change in the years, we went from 2000. I hope my pen is showing this because I've got a menu right here that I can't see it. This should say 2010, and this should say 2000. I think I'm in the right spots. So we do 2010 minus 2000. If you do that subtraction, you're going to get 45,864 divided by 2010 minus 2000 is 10. If you do that division, you're going to get 4,586.4. That is our slope. This is the rate of change in the population per year. That's what the slope is representing here, because we're talking about change in population versus change in years. So that's going to be part of question 2 that I will have to scroll down and erase everything to get to, so let's hold off on that. But that's our M. For our B, we just talked about a second ago, we didn't do an example, but we did one last time, how as long as you have a point and a slope, you can plug those in to find the B. So remember, we're going for y equals mx plus b. So we're going to plug a number in for the y, we're going to plug a number in for the m, which we just found, and we're going to plug a number in for the x, and then we're going to be able to algebraically solve for b. Well, what y and x do you plug in? You could plug in the 49,000 with the 2,000. I can't actually circle that, unfortunately, because menus. Or you could plug in, so pretend like there's a red circle around 2,000, or you could plug in the 95,000 with the 2010. So pretend there's a blue circle with the 2010. It doesn't matter which points you use. It doesn't matter which points you use. At the end of the day, you'll get the exact same answer. Now, if any of these have a 0 in them, that's the one I would use, because zeros are easy to plug in, but we don't have that here. I think 2000 is easier to plug in than 2010, so that's what I'm going to do. Let's go back to red. Okay, so I'm going to plug in the 2010 numbers. I know this is in red, so just please ignore that that's red. I'm using these numbers. So that's the y value. 95,696 equals the m, which we just found to be 4586.4, times the x value, which is the 2010. What am I doing? I said I was going to use 2000, but I circled 2010. Let's just go with it. I already said it doesn't matter. I made myself a liar. I said I was going to use the 2000 numbers. We're going with 2010. So that's times the x value, which was 2010. And then plus, we're not plugging a number in for b, so we leave it alone. Again, at the end of the day, when I solve for b, if I had plugged in the 49,000 and the 2,000 into here and here respectively, here, you would end up with the same b. All right, I am going to have a difficult time putting the calculator on the screen at the same time, so you're just going to have to trust me that these numbers are right. 4586.4 times 2010, please try this on your own, is going to be 92, why does that look wrong? 664, let me double check that, 4586.4 times 2010. I'm just not used to plugging in those numbers. I usually do the 2000, that's why. So that's 95696 equals, this number is 9218664 plus b. Then to solve that, all you do is you subtract the 9 million number on both sides. So the minus 9218664, just doing very basic algebra here, which tells us that, and if you do that subtraction, you're going to get 95696, 95696. You're going to get negative 9,122,968 is equal to b. So we have our m, we have our b. We're going to plug those numbers in to the m and the b to get our model. So our final answer, the equation, the model, is y equals, the m was the 4586.4. Sorry if you hear that siren. They heard I was doing math, so they're coming to get me. 4586.4, x, that's the m and the x. This was the slope. We found the slope by doing 2 points and finding their changes, their rate is a change. Then, because the b is negative, I'm actually going to write a minus here, and there's the 9,122,968. If you really want to comma here as well, you can do that. This is the answer. That is the equation of the model. This is a very common way to find an approximation to modeling some population over a short period of time. This is not a great model, but it would have been if we had done it a slightly different way that we'll do later. interpret the slope in the y-intercept. So unfortunately, I'm going to have to clear my screen. So when I clear my screen, I'll scroll down and I'll just write that stuff again because I've got it. I've got the numbers in front of me now. So clear, scroll, go back to annotate, interpret the slope and the y-intercept. All right, so the slope is slope of 4586.4. I just want to write that down so you see it again. It means that the population is increasing because it's positive by 4,586.4 people per year. Now you might be saying, why didn't you just say 4586? Because we're dealing with a large population. If we were only dealing with a dozen or 100 people, I would round that to the nearest whole. But when we talk about very, very, very large values with people, we keep the decimal. So that's the slope. The y-intercept, or the initial value of minus 9,122,968, means that the population at, now remember, y-intercept means the initial amount, which means the zero. So at year zero was negative 9,122,968 people. What? Huh? At year zero, there were negative 9 million people in Palm Coast, Florida? Guess what? That doesn't make sense. I said last class that y-intercepts, when we're dealing with real models, do not always have to make sense. And I even alluded to the fact that we're going to deal with these two versions of population dynamics, one where we just use regular years, so year zero was 2,020 years ago. And sometimes we'll use a year since, like that year since 2000, where year zero in that sense would actually be the year 2000. Year zero in the model, in the real world, relates to the year 2000 then. And it doesn't have to be year since 2000. I can make a model where it's the year since 2005, or the year since 1984, or the year since 2020. So this does not make sense because population or linear population models are awful for very long periods of time. On top of that, Palm Coast, Florida didn't even exist. It would not make sense to model a population any year before it actually existed. That's like going into negative years for that region. So also, this town didn't exist in the year zero. Can't model that way. How are we on time? Okay. Number 3, let me go back and write the equation from number 1. It was y equals 4586.4x, which was the slope, and then minus the 9,122,968, which was the initial amount of people, which we said didn't make sense for various reasons. Can't have negative people. Can't model a population when it didn't exist. Don't want to do linear models for these ridiculously long amounts of time. So number 3, use the values in the table to determine the line between 2 points of Palm Coast, Florida, where x is the number of years. And this is not correct. This is a typo in the textbook that I wish they would fix, at least in the electronic version. X is supposed to be the years since 2000 now. That's a major difference. They've really screwed up that problem by missing that detail. It's not just years, it's years since. If they said x equals years, then number 3 would be the exact same problem as number 1. Not the point of this. So now we want to take this to a shorter time frame for modeling the population, which I've already alluded to is generally better for lines. You don't want to do a population model for more than like 30 or 40, 50 years with lines. It's a terrible idea. All right, so we're going to use the exact same 2 points, which I'll just write them up here. But now we're doing years since 2000. So what you're going to notice is that the year 2000, which was originally in that table, is now going to be a 0. The year 2000, when we're using X being the number of years since 2000, is 0. And the population then was that 49,832. And then the other point was the year 2010, which would be 10 years since 2000. Oh boy, that was not what I meant to do. Okay, that worked somehow. And then this population was the 90,000 something, 95696. I don't really want this comma here. That looks awful because of the comma for the point, and you can see why I just deleted that comma. So I just wrote these as coordinate pairs. They're literally the same thing from the table, but now the year 2000, we've turned into 0 because our model is saying, hey, 0 is now just 20 years ago, currently speaking. And the same thing for this. We're going to do the exact same thing as in number 1. We're going to find the slope by doing the rates of change. We're doing the y's on the top, the x's on the bottom. We're doing new minus old. So we go 95696 minus 49832, literally the same subtraction. In the bottom, instead of doing 2010 minus 2000, because x is now representing the year since 2000, our x values are 0 and 10. So 10 minus 0. So the bottom looks different, but what's interesting is when you do the subtraction, you get the same value as last time. That's actually exactly what always happens when you change from a total years overall to a year since model. The change in years won't matter where your time reference starts, but something will change later, trust me. And the top is the same subtraction. That was the 45864, which doing the division ends up giving you exactly the same slope. This is a very important concept. No matter what type of model you use, a years or years since, the slope will come out to be the exact same. But spoiler alerts, the intercept will not. All right, so to find the y-intercept, I'm going to change colors just for make this a little prettier. We're doing that y equals mx plus b again. We're going to plug in any number for the x and the y that we like out of these two options. We can do the 0 and the 49,000 or the 10 and the 95,000. The m is the same m before. We're going to plug that in there, and we're going to find the b. Now, I'm going to use this point, definitely. I mentioned earlier, if any of them ever have a 0, which is pretty common in a year since model, that's going to be the easier one to plug in. So the x value is the 0, the y value is that 49,000. So we go 49,832 equals, the m was the 4586.4 times the x, which is 0, then plus the b. Again, this is the y value, this is the x value. I did not plug in the same y and x value as you saw me do in number 1. Again, I could still plug in the 10 and the 95,000 instead. You will get the exact same value of b, but your algebra will be more difficult. You'll have to do the same type of algebra as last time, whereas this time, since anything times 0 is 0, you just get 49,832 equals b instantaneously. So this is the initial amount. So our model is y equals 4586.4x, so there's the variable amount, plus 49832, there's your initial amount. Oops, let's try that again. Same slope, different y-intercept. 8, that looks like I wrote a wrong number. 49832. It looks like I wrote a wrong number because I did write a wrong number, to be honest. I wrote the 8 twice. You know what's awesome about this model? The interpretation of the initial value makes complete sense. This does not say at year 0 the population was 49,832. This says 0 years since 2000, the population was 49832, which makes complete sense because look at this. It's exactly what we were told. So that Y-intercept makes much, much, much more sense. And I'm about to write those interpretations. Let me do this. Question 4, if you flip to the next page, says interpret the slope in Y-intercept. So question 4 is exactly the same as question 2. So what I'm going to do is I'm just going to erase the block for question 2 here. And I'm going to put 4 here instead. So now I'm just saying we're doing question 4. I'm not saying question 2 is disregarded. I'm just going to put the answer to number 4 here so I don't have to erase what's on the screen. I'm trying to help y'all out. All right, so interpret the slope and intercept. I don't have to write the slope since you can already see it. So we're going to say that the population of Palm Coast, Florida, PCFL Palm Coast, Florida, was increasing by 4,586.4 people per year. Oh, we can't say per year. We got to say per year since 2000. And it makes more sense to say it that way. We don't want to say per year because then you might say, all right, so in 1500, we were increasing by 4,586 people a year. In the year 17, which was a long time ago, the population was increasing. It wouldn't make sense then. But if you're talking about 2001, 2002, 2009, 2030, this will be a lot closer to the actual value. Now, I'm not saying it's doing this exactly. I'm saying this is kind of like an average. Then the intercept, we can say that in the year 2000, the population, so the year 2000 is 0 years since 2000, the population was 49,832, which makes perfect sense. Your interpretations for population models tend to make more sense when you look at a shorter time frame, when you use a year since. When you're using years and going all the way back to the year 0, 20 years ago, it is much, much, much more difficult to model population dynamics. Even exponential equations aren't that great when you look at 2,000 years. Lines are awful because if you actually went through and looked, I don't want to erase anything. If here is 2000, the population was basically 0, 0, 0, 0, 0, 0, 0. I mean, maybe there was like 100 or 1,000 people there before America came over and did what it did. So, you know, hundreds of people, thousands of people, something like that. Just pretend like this is a little higher, I guess. But then all of a sudden, it just explodes for Palm Coast, Florida. So trying to use a line to approximate this is a pretty awful model. So if the black represents the actual people over time, the red would be a linear approximation to it, which is just trash. All right, so there we go.
All right, so we're going to call it there. The next example that I was going to have loaded was going to take probably more time than we had for the rest of class. So just want to go ahead and call it a day there. Again, your reminders for due dates and such coming up. 4.4 due on the, well, today. 5.1 and 5.2 due on the 4th, 5.3 due on the 6th. 5.1 Excel file for lines due on the 6th, video quiz 2 due on the 6th. Remember, there's a spot to download that assignment and then to upload your work. And then your project is also due on the 6th, which you should have been working on for the past month or so. If you are in my MDE 54, remember that I said I have a schedule conflict today, so that class is not going to be held, but Math 154 will still be held on this coming Monday, as will MDE 54. So besides that, as always, if you have any questions, shoot me an email. Make sure you read ahead in the notes to share. We'll pick up on 5.4 next time. Besides that, have a good weekend and enjoy the slightly warmer weather we're supposed to have. Take care.